The gradient of a function of two variables is given by this vector of partial derivatives. From a previous video, we discussed that the gradient is actually the derivative of a multivariable function. In addition, in some other videos, we've already talked about certain differentiation rules, so linearity, product rule, chain rule, etc. What we're going to do here is talk about geometric properties of the gradient. Now, if you take a look at the geometric definition of a dot product, you'll be able to rewrite the directional derivative as this expression. Remember that u hat is a unit vector, so it has a length of 1. So what we're finding is that the directional derivative can be represented in this way. So this directional derivative is maximum when the cosine of this angle between the two vectors is equal to 1. So that means when theta is equal to 0, and that means when gradient vector and u point in the same direction. That's when your function has the maximum rate of change. The maximum rate of this directional derivative is simply just the magnitude of that gradient. The directional derivative will be a minimum when the cosine of theta is equal to -1, its minimum value. That means that the angle between them is pi, and that tells you that the gradient and this u hat point in opposite directions. And then the minimum rate of change of your function along that direction is simply just the negative of the magnitude of the gradient vector. And you will have no rate of change if this cosine of the angle between them is 0. And that tells you that the angle has to be pi over 2, which then tells you that the gradient and this unit vector have to be orthogonal to each other. We are going to visualize this with an example. And so this will be x squared plus 3y squared plus 4. And we're going to talk about the point 1, 1. Now, at this point 1, 1, the height of the function is simply going to be 1 squared plus 3 times 1 squared plus 4 is going to be 8. If we were to draw this paraboloid, it has a gap. It's raised above the xy plane. And we are talking about the point 1, 1 here. And right up there is the point that we're interested in. At the point 1, 1, 8, in what direction do we move to ascend or go up on the surface at the maximum rate? If I were to look at this picture, I can travel in any direction along this surface. And some of those directions will take me up, and some of those directions will take me down. But in which way should I go so that I have the maximum increase in my height? I should travel in the direction of the gradient at that point 1, 1. So if you want to think about it here, the gradient is just given by the vector of partial derivatives of this function. So I need to calculate the partial derivatives of this expression. So this is going to give me a 2x, whereas the y partial derivative of this expression is going to give me a 6y. And so the gradient vector at the point 1, 1 is simply going to be the vector 2 and 6. The length of this gradient vector is the length of 2 squared plus 6 squared, which is the square root of 40, which is going to give me 2 root 10. Here's the unit vector u. It's the gradient of f over its length, and it's essentially 2 taken out of this vector. So I'll get a 1 and a 3. 1, 3 divided by 2 root 10. Those will cancel out. I'll get 1 over root 10, 1 and 3. So it's just a multiple of the vector 1 and 3. So it's a vector right here that kind of looks like this. This is the direction of u. And if I were to go in that direction right there, I would be moving up the curve with the maximum rate. This is where the function increases the fastest. And so the maximum rate of ascent is simply just the magnitude of the gradient at that point, which is 2 root 10. Now, at the same time, the direction for the maximum rate of descent, which means going down the function, is simply the negative of the gradient. So you can take the unit vector to be negative 1, 3 over root 10. Any multiple of negative 1 in root 3 will do. If we take that same picture and redraw it at the point 1, 1, now instead of going outward, if I go inward, if I move this way, what it's going to do is tell me that I'm going to be moving down the function there. And that's the important difference. One direction tells you to move up, and the other direction tells you to move down. Now, another thing that we're going to talk about here are the level curves of my surface f of x and y. A level curve is when you set the value of that function equal to some constant. In terms of a picture, this is like saying take your function, set it equal to some height, z is equal to a constant. Now, this is going to produce a curve of intersection with your surface that represents the curve of constant height. If we were to take this and project it down, there will be some curve like so, and you can talk about a parametrization of this curve, and we would call it this r of t, and it's going to have some coordinates x of t and y of t. When we talk about level curves, we're saying take your function, put it right above this green curve, and talk to me about the value of the function there. If we were to take those points given in parametric form and put them inside of my function, I can take a derivative with respect to t, because t is going to be the parameter here. So if f is differentiable, we are guaranteed that the partial derivatives of that function must exist, so we are able to use the chain rule. And the chain rule is going to tell me this will be df dx times dx dt plus df dy, dy dt, and that's going to have to be 0. The gradient vector times the vector of derivatives x prime and y prime, or the gradient vector dotted with the derivative of the parametrization. The gradient is always orthogonal to the tangent of the curve given by r of t. So if we think about it back in terms of that picture again, there's my curve, my function up here, and at any point on this curve, there's a tangent direction, r prime. The gradient vector will always be perpendicular to that tangent. Now, wherever you move along that curve, the gradient vector will always be orthogonal to the direction of that curve. Another way of interpreting this is if you walk along f of x, y equals k, if you walk along that curve, the directional derivative, which is given by this, is going to be 0. And that makes sense. No change in height, because the height of f is constant. So this is an interesting fact that we're going to leverage throughout this section here. Now back to our example. If I had that same paraboloid, x squared plus 3y squared plus 4, I already know that the gradient vector was given by 2x and 6y. The gradient vector at the point 1, 1 was just the vector 2 and 6. If I talk about the level curve, z equals 8, take this paraboloid. There's the axis there. If I intersect this at the height z equals 8, it's going to trace out some curve. So if I take the equation of my function and set it equal to 8, I'll have x squared plus 3y squared is 4, x squared over 4, 3y squared over 4 is 1, or x squared over 4, y squared over 4 thirds is equal to 1. This means I'm going to have an ellipse in the xy plane. The parametrization of this ellipse is 2 cosine of t, 2 over root 3 sine of t. You can go back to your videos from before to learn about how to parametrize an ellipse. The gradient of the function will always be perpendicular to that vector at any given point. the derivative is going to be negative 2 sine of t, 2 over root 3 cosine of t. Now, at the point 1, 1 corresponds to this system of equations. 2 cos is 1, 2 over root 3 sine of t is equal to 1, cosine of t is a half, sine of t is root 3 over 2. You can use your special triangle results to figure out this happens when t is pi over 3. The tangent vector at pi over 3 is going to be the vector negative 2 times root 3 over 2, 2 root 3 times a half. So that's negative root 3 and 1 over root 3. And if I were to take the gradient at the point 1, 1 and dot it with this tangent vector, what I would find is I'd have a 2 and a 6 dotted with negative root 3 and 1 over root 3. I would get negative 2 root 3 plus 6 over root 3. This is going to be negative 2 root 3 plus 2 times 3 over root 3, which is going to be negative 2 root 3 plus 2 root 3, which is 0 as expected.